Good morning and good evening, everyone. Thank you again for joining us in today's seminar. This is our 18th joint seminar between Binghamton University and VIT. Today, we are very delighted to have Professor Raja Sellappan from VIT. Dr. Raja joined Vellore Institute of Technology as an associate professor in 2017. He earned his Bachelor of Engineering in 2002 from Barathiyar University in Tamil Nadu, India, in electrical and electronics engineering. In 2008, he received an MS degree in electrical engineering, specialized in molecular electronics and system design engineering from Linköping University in Sweden. In 2013, he earned a Ph.D. in material science from Chalmers University of Technology in Gothenburg, Sweden. His research interests include solar energy conversion, solar cells, solar fuels, 2D materials, photocatalysis, photoelectrochemistry, and flexible optoelectronics. So we are very delighted to have Dr. Raja join us today to talk about his research in the area of unassisted solar water splitting to hydrogen using tandem architecture. And before I turn it over to Dr. Raja, I would like to remind our participants that during the week of March 14th in the US, the time will be changed because of the daylight saving. So starting the week of March 14th. So for that week, the adjustment will be made to our schedule. And for the US, it will still be at 8:30 a.m. US Eastern Standard Time. But in India, it will become 6 p.m. India Standard Time. So I just wanted to remind you all about this change. And also, we will include this in future announcements when we announce the seminars. And also, I'd like to let you know that halfway through this presentation, I'm going to have to step out to another meeting, but my colleague, Dr. Fudaneng, will moderate the session for the Q&A portion at the end of this presentation. I will be just presenting a 15-minute presentation during that meeting. So I will probably come back fairly quickly as soon as that meeting is over, but my colleague, Dr. Fudaneng, will help moderate the Q&A session. And without further ado, please join me in welcoming Dr. Raja to our webinar series. Dr. Raja, I'll turn it over to you.
Thank you, Professor Muhammad, for your nice introduction. So, good morning and good evening, everyone. And hope my PPT is visible.
Yes.
Okay. So I'm going to talk about today is on unassisted solar water splitting to hydrogen using tandem architecture. So we have started this work a couple of years back, and this is one of the funded project by the DST funding agency from India. So I'm going to show you some of the ongoing results from this work. Apart from this title, I'm also going to shed some light on flexible perovskite solar cell. Okay, so even though the title is about unassisted solar water splitting to hydrogen using tandem architecture, so second part of my talk will be a little bit about the solar cells as well. So with no further delay, let me get started. So why we need this solar hydrogen? What is solar hydrogen? So I will give some basic introduction, and then I will just some of the ongoing research that we have produced in our lab. The first thing is that, as you may be aware of that, we just derive energy currently mostly from fossil fuel sources such as coal, natural gas, and oil, and these account for more than 85% of today's energy production. So even though as per this statistics, these fossil fuel reserves, okay, can last for another couple of 100 years. So when you just keep on burning these fossil fuels, we just increase CO2 in the Earth atmosphere, which in turn, okay, causes global warming. And you know what is the problem with this global warming? Already we are facing a lot of consequence based on this global warming. So one alternative ways, or the best way, is to use the radiation or the energy that is coming from the sun. So even though there are different ways actually just to kind of tackle these issues. So in this presentation, I'm going to focus on how to produce hydrogen using solar energy. And in this solar hydrogen cycle, if you just look at, we just capture the solar light and convert to hydrogen. And this hydrogen can be stored in a kind of tank or reservoir, either in the form of gas phase or in the form of liquid phase. Okay, so depending on the situation. And this hydrogen can be used actually to drive your automobiles, either using hydrogen based combustion engine or using fuel cells. And also using this fuel cell, we can also power our home. Okay, for domestic use also, we can just convert this hydrogen back to electricity so that we can just also power home. So, and also hydrogen is used as a chemical feedstock for a lot of okay new lot of industry chemicals. For example, ammonia synthesis is one of the important thing where we use hydrogen as a raw material. So we can also use this hydrogen also for some industrial chemical production as well. So when you just convert this hydrogen, when you use hydrogen as fuel, when you just convert back to some energy form, so the byproduct that is produced from this hydrogen is only water. So there is no CO2 produced here. In this way, we can just protect our environment, and also the energy that we just convert is also from the sun light. Okay, so it is also renewable. So in this way, we can just at least have clean and green energy. Okay, so that we can just tackle this global warming issues. But there are some challenges ahead. Okay, that's the reason that we are doing a lot of research work. Okay, so there are different ways actually to produce hydrogen from the solar energy. So even though there are different routes, okay, here I'm going to focus on this one, photoelectrochemical solar energy to hydrogen. So if you just take this photolith system, okay. So for example, at present, so you can convert this solar energy to hydrogen in different ways. One of them is this photovoltaic combined with electrolyzer system. Both photovoltaic based on silicon based solar cell and electrolyzer, they are mature technologies. Okay? So one can combine this photovoltaic plus electrolyzer. Okay, the idea here is that you just use solar cell, solar energy to electrical energy. Then we just use that electrical energy just to feed into this electrolyzer unit to convert water into oxygen and hydrogen. And the problem with this system is that we need two different setup, one for solar cell, another one for electrolyzer. And if we want to just provide energy for mass production, so this is quite complex. And also if we just calculate the cost per hydrogen, okay, so it's it's not that much cheaper than other system. It's quite a bit expensive. So the second one is that here it's kind of we are using photoelectrochemical cell to convert this solar energy directly into chemicals in the form of hydrogen. So here normally a semiconductor or semiconductors are employed directly in aqueous environment where the light is illuminated on this semiconductor absorber. So that solar energy directly converted into chemical energy. So here solar energy to some chemical reaction is taking place. In this case, water splitting into hydrogen and oxygen. And there is also one more system available. This is actually solid system, solid photoelectrodes, and sometimes people also use powder form of electrodes, or that is powder form of photo absorber material. So cost wise, if you just compare, this is the cheapest one compared to among all three techniques. However, in these techniques, because in the end we want to separate hydrogen and oxygen, and we want to use that hydrogen to do some kind of use it for some application. So the separation of gases here it's a bit difficult, and also regeneration of this catalyst is also a bit problematic. So one of the optimized technology, okay, to convert solar energy to hydrogen is, I would say, that this photoelectrochemical cell. So my focus here will be on this photoelectrochemical cell-based hydrogen generation. So if we just take a typical photoelectrochemical cell, okay, so we use one of the electrode is called anode. So if it is based on semiconductor absorber, then it is called photoanode. So here normally oxygen evaluation reaction is taking place. When you use this photoanode, so here oxygen is produced. Another electrode is called cathode. So it may be also under semiconductor, or sometimes it may be platinum, okay, in the form of counter electrode. Here normally hydrogen evaluation is taking place. So we need electrolyte, so to just kind of have high conducting path between, because when it just generate the electron here, then protons need to be transferred from here to cathode side. In that case, the liquid medium should be high conducting enough. So if you use for water application, if you just use semiconductor as photoanode, it should be n-type semiconductor. And similarly, if you use photoelectrodes at the cathode side, then it should be p-type. So if you just take a semiconductor and if you keep it inside an aqueous environment, okay, so we need to kind of fulfill certain basic requirements, because in this case, we keep the material in liquid environment. If you want to just use it for commercial application, so they expect that this system should last long for at least 10 years. So in such a case, the material should be stable enough. So that is one of the important criteria, that it should be chemically stable, and also, okay, the availability of material should be also high. So earth abundant material one should use with low cost. Apart from this, one has to have suitable band edges. Okay, and the last point is that this photoelectrochemical system should produce at least 10 milliamps per centimeter square of photocurrent, because for practical application, the Department of Energy has said the efficiency that should be produced from such systems should be above 10%. Okay, to achieve above 10% efficiency, that photoelectrochemical system should produce at least 10 milliamps per square centimeter of photocurrent. Since we just employ a semiconductor and light is illuminated on the semiconductor, so you can see there are three fundamental processes taking place when light interacts with the semiconductor. The first is light absorption and generation of these charge carriers. So once the charge carriers are generated, they need to be separated and transported to the interface. So once they are transported to the interface, the next process is that they need to be transferred to the electrolyte medium, where the desired chemical reactions are taking place. So these are the important fundamental processes in any photoelectrochemical systems. Apart from this fundamental process, so we also have some kind of competitive process. So what are the competitive process means? So as soon as electron voltages are generated, so there is a high chance that this electron will recombine with electron hole at the valence band. So it will release that energy either in the form of light or sometimes in the form of heat. And no material is perfect, so you also have some defects present in the material, either in the form of bulk defect or in the form of surface defects. Okay, so there is a certain probability that these generated charge carriers, okay, will recombine or trap in this defect state, so they lose that energy. In some cases, what happens in presence of light and presence of aqueous medium, okay, so these photo-generated charge carriers will degrade the material, self-degrade the material. Okay, this process is called photocorrosion. So, so there are different kind of unwanted reactions, okay, taking place. One has to minimize, okay, this unwanted process while designing the photoelectrochemical system, so that one can achieve better efficiency. So there are some strategies one can employ to improve this fundamental process. I'm going to highlight some of the important, okay, process. Okay, that are used in the literature. For example, I just told you the first process that is taking place is light absorption. So to just improve the light absorption, for example, if you just have nanostructured materials, okay, for certain nanostructuring materials, so when the light interacts with nanostructured materials, so there is a chance for multiple scattering effect. So this multiple scattering of light with the help, okay, in presence of this nanostructure material, okay, will redirect light, okay, again to the material. So this will prolong the light optical path inside the material, so which will eventually increase the light absorption. Or instead of using single semiconductor material, if we just use complementary semiconductor with different band gap materials, so one can also maximize the light absorption in the entire solar spectrum range that we receive from the sun. So another important thing that is done in the literature is that band gap engineering. So given for a given material, if you just do something like a doping, okay, or adding some kind of impurities to just modify the band gap, so you can also tune the band gap, so thereby tune the light absorption properties. When it comes to charge separation and transport, because once the light charges photo carriers are generated, okay, they need to be transported. In this case, the conducting properties of material plays an important role. So to improve the conductivity, okay, and okay, doping is one of the process to improve the conductivity. Or another way just to improve this charge separation, because our task is these charge carriers should be separated, okay, somehow without getting recombined back with this electron hole. So if you just introduce heterojunction with suitable band gap materials, this heterojunction also will just kind of separate the charge carriers if the band offset is suitable, so that electron will move to one side and holes will move to another side. And one of the important thing to just separate charge carriers is built-in electric field. Okay, so this built-in electric field will just separate the charge carriers in the right direction, and as long as this charge carrier is generated close to this what is called decreasing layer width or built-in electric field region, or close to this minority carrier diffusion length, so whatever the charge carriers that are generated close to this decreasing region or built-in electric field region, they will be separated efficiently. And also nanostructuring also plays an important role, because when you just make nanostructure, so you have high surface area to volume ratio, you can, okay, uh, optimize through synthesis this the diameter of the nanostructure, so that this diameter will be in such a way that that will match with the diffusion length of your charge carriers. So in that case also one can easily separate the photo generated charge carriers. So once the charge carriers are transported and separated, okay, they need to go to the interface, where interfacial charge transfer is taking place from the semiconductor to this aqueous medium. So normally not all semiconductors are catalytically active. So, so now to improve this catalytic reaction, so one can add co-catalyst, okay. So when we add co-catalyst, okay, that will also improve charge transfer, which will further increase the reaction rate. Sometimes most of the semiconductor, if you just look at, okay, the surface are not terminated properly, so you have more dangling bonds. So by just properly, okay, terminate this surface dangling bond with some passivation layers, so that will also minimize this trapping state at the surface, which will further improve this interfacial charge transfer. So another important thing is that we need to increase the active site. So to increase the active site means it will also yield more products. So for that, nanostructure again comes to picture. So you just increase the number of active sites. So these are some of the processes that have been used in the literature to just improve the basic process. So so to just split water into hydrogen and oxygen, so we need to consider two things. First one is thermodynamics. So the thermodynamics tells you whether the reaction is possible or not. The reaction happens, that is decided by thermodynamics. So to split water thermodynamically, we need a voltage of 1.23 volt, or you need a material with a band gap of 1.23 volt. the thermodynamics, one should also consider the kinetics, that is how fast the reaction taking place. So even the material is thermodynamically favorable, if it is kinetically sluggish, so it has negligible electrochemical reaction, so you will not get any kind of output. Okay, so one should also look into this one. So most of the semiconductors that we just take here, they are kinetically slow, so they add some kind of extra layers to just to boost this kinetic reactions. So, so theoretically, if you just look at the incoming solar spectrum, okay, so we need something close to 1.23 volt, but because of some losses, okay, so we need to apply potential, or we need to choose semiconductor with a band gap of about 1.6 to 2 volt. Somewhere close to here, we need to choose semiconductor so that it can just efficiently drive this water redox reaction. So the difference between this practically applied potential to the thermodynamic potential is referred to as over potential. Okay, so the extra potential that we apply, so in comparison to thermodynamic potential, is called over potential. So that is considered as losses. So if you just look at this seminal work done by Fujitsu and Honda with the titanium dioxide as the semiconductor material. So the titanium dioxide is the best material for this water splitting reaction because it is chemically stable, okay, in different environment. But it has a band gap of about 3.2 electron volt. When you just look at 3.2 electron volt, okay, with the number of photons, the number of photons that are reaching, okay, to this energy scale is very, 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 okay, small, less than 3%. So obviously the photocurrent generated by this one will be very, very small, and the final output, the efficiency will be less than 2%. So that's the reason that one has to choose the material that is close to this visible region. So close to 1.6 to something close to 2.6 volt. So, so if you just take a single semiconductor photoelectrochemical system, no semiconductors, okay, so far, okay, have fulfilled this requirement of being good photocatalyst. It doesn't fulfill all the basic requirements, and also, so we didn't get this 10% factor for hydrogen efficiency. So one alternative to just improve this solar to hydrogen efficiency is just to combine different photoelectrochemical system. So the stacking of different photoelectrode system is called tandem system. So one can just play with the tandem system to improve this practical solar to hydrogen efficiency. So while designing this tandem photoelectrochemical system, so one thing is that the water redox reaction, that is splitting of water into hydrogen and oxygen, should be taken only from the solar energy as the input. No extra energy should be provided from the power supply. So that's one thing. And also, as I told you before, that we need to choose earth abundant material, and also it should be very stable. So in that aspect, okay, uh, there are different ways actually you can just kind of design. So if you just look at the literature, one thing is that they just have this solar cell with this photoelectrochemical system. So this is one way actually, and because we have some kind of matured solar cells available, the way actually to combine photovoltaic anode system. And the second one is called monolithic. Monolithic means you just make all the electrodes in one on one substrate. That is in this case, so they have this both p-type and n-type photoelectrodes on this conducting substrate. So since it is fabricated on one substrate, okay, this is called monolithic tandem structure. Another type that is used in the literature is called Xrd. So in this case, you have photoanode on one side and photocathode on the other side, so that are connected by external conducting wire. So in our work, actually, we are going to focus on these Xrd systems where we just use the N-type semiconductor at the anode side and P-type semiconductor at the cathode side. And so what is the advantages of what are the advantages of having such a tandem system means one example I would give is that if you use a single semiconductor, so the single semiconductor will absorb light, for example in this, if you use a double absorber, dual absorber, you can just improve the okay absorption efficiency, so that you can just cover almost the entire spectrum of incoming solar radiation. So that's one thing. And the second important criteria is that in such Z scheme, okay, so I'll just show you in a minute. Okay, so in our work, actually, we prefer to work with the semiconductor oxide materials because semiconductor oxide materials are cheaper, and also you have more availability of semiconductor oxide materials, and it's already oxide, so it is all okay. So it will be more stable in aqueous environment. So for that reason, we just choose some well-documented oxide material that is already used in this single electrode photoelectrochemical cell. For example, so in our work, actually, we are going to the work that we are doing right now is based on this cuprous oxide and this bismuth vanadium oxide. Okay, I'll show you why. But you have different combination of oxide materials, so one can play with the different oxide materials. Okay, so based on the band gap values, because so one important thing is that beside the band gap value, so this valence band and conduction band quotient should be in such a way that conduction band edge should be higher than this hydrogen redox potential. So if it is higher means when you create electrons, so this electron can easily transfer to this okay to the electrolyte medium and reduce water. Similarly, for valence band, the valence band edge should be, so it should be 1.23 to split water theoretically. Okay, imagine this is 1.23 here. So this valence band edge should be okay more below than this water oxidation potential. So when you have this kind of band position, so hole can easily transfer from lower okay potential to higher potential side. So in this way, you can just easily oxidize water. So that is one of the important criteria while choosing this photoelectrode materials. So to just choose a combination of photoelectrodes for this system. So I told you before that for photoanode we need to choose N-type, for photocathode we need to choose P-type semiconductor. And apart from that, if you imagine that this is the electrode, okay, so the light is passing through this electrode first. If we just define it as band gap is 1, top electrode, and this is the imagine that this is bottom electrode, so the band gap is let me define it as Eg2. So we need to choose this semiconductor for photoanode and photocathode in such a way that the band gap of this top electrode should be higher than the band gap of this bottom electrode. So then only whatever light that is not absorbed by this top electrode will be absorbed by this bottom electrode. Okay, in this way one can just maximize the light absorption. Okay. And there are some theoretical prediction available to just identify the right materials. Okay, so even though if you just look at, one can just achieve close to 22%. Okay, so this theoretical prediction actually was done by Kevin Sula from EPFL Switzerland. Okay, so they just assumed something like the system should produce loss of something like 2 volt. By considering that loss, they could achieve efficiency of more than 22% for this tandem system. So for 22%, you need to choose the top electrode, the photoanode band gap should be 1.8 and bottom electrode band gap should be 1.15. Unfortunately, if you just find the semiconductor that are close to this one, okay, so we have this the best elemental semiconductor that we use in semiconductor for electronics, but these semiconductors are not stable in aqueous environment. Okay, so that's one of the problems. So in this work, actually, we just fixed with some oxide materials. So we just uh, took bismuth vanadium oxide as photoanode and cuprous oxide as the photocathode. So for bismuth vanadium oxide, the band gap is 2.4 volt, and for cuprous oxide, the band gap is 2.1. So for this combination, one can achieve the maximum efficiency of close to 7 to 8%. But it's really challenging to just get this theoretical efficiency. So since these materials have been studied very frequently, and we have some well documented literature results available. So our task is just to engineer these two materials in a proper way so that one can just achieve better efficiency from the system. So apart from this semiconductor photo absorber, we also add some co-catalyst to just catalytic reaction. So for bismuth vanadium oxide side, we just use iron oxyhydroxide, and for photocathode side we use molybdenum disulfide, and also we also play with this surface passivation layer. So we wanted to add titanium dioxide as passivation layer using atomic layer deposition. So apart from titanium dioxide, we also work with the carbon. So the result that I'm going to show you, okay, from this structure is actually done by Mr. Raman. He is working as junior research fellow in our lab. So I just skip this part, okay. So there are well documented literature results available, but bismuth vanadium oxide has a band gap of 2.4, and it's an n-type semiconductor. So even though it has a suitable band gap for this water oxidation, that is to split water into oxygen, it also has some drawbacks. But for the last few years, there are a lot of new ideas actually have been proposed to improve these disadvantages posed by bismuth vanadium oxide, because theoretically bismuth vanadium oxide, if you have 2.4 electron volt, it should produce photocurrent of 7.5 milliamps per cubic centimeter, okay, per centimeter square. So with the help of lot of optimization, okay, so now we can just move close to 6 milliamps, okay, that is close to theoretical value. So but of course this one with the additional complexity in the structure, okay, but it is possible to just achieve theoretical photocurrent value by just proper optimization. So this is one of the best photoanode material, okay, so to date as a photoanode in this photoelectrochemical system. So here we prepared this bismuth vanadium oxide by spin coating method, okay. So after spin coating, we just annealed the structure at 500 degrees Celsius because we wanted to have some crystal structure. And after this bismuth vanadium oxide preparation, this co-catalyst FeOOH was prepared by this chemical impregnation method as per this procedure. And similarly, we just work with cuprous oxide as photoanode, because this is also one of the standard material in photoelectrochemical community. And this cuprous oxide has a direct band gap of about 2.1 electron volt, okay. So the top electrode is 2.4 electron volt, and this bottom electrode has a band gap of 2.1. So it's a good choice to just combine these two systems. And also, even though okay, they have some good properties, okay, in presence of water, okay. Uh, so when you just shine light on this cuprous oxide, so there is high chance that this material will self corrode, okay. So that can be actually okay overcome by adding some kind of suitable protection layer, okay. So for this kind of material, people used already this aluminum doped zinc oxide or titanium dioxide, okay. So that has some positive response that is minimize this photocorrosion. So here we prepare this cuprous oxide by electrochemical method. And then we just, for cuprous oxide, okay, so we started with carbon as a protection layer instead of titanium dioxide. So we are working on also titanium dioxide as well. So So in this work, what I'm going to show you is that we just kind of prepared carbon, okay, on top of this glucose oxide, and then we just added this co-catalyst MOS2. MOS2 was prepared by hydrothermal method. So I'm going to show you some of the basic characterization results, okay. So from the Xrd spectra, okay, normally we use Xrd just to analyze the crystal structure. Tandem oxide, we wanted to have this monoclinic phase of oxide. Okay, so what we got is actually was monoclinic phase. So here actually we prepared three samples, one with the bare bismuth vanadium oxide. The second one is with molybdenum doped bismuth vanadium oxide, just to improve the conductivity because bismuth vanadium oxide, so being a semiconductor oxide material, so okay, it has poor charge transport. So we just dope this material with molybdenum. And the third one is actually, this is actually with the FeOOH, okay, sorry for this wrong labeling. So we also added this co-catalyst, okay. Uh, so in all these cases, what we got was actually this monoclinic sealite phase of bismuth vanadium oxide. Similarly, for cuprous oxide, from the Xrd and also after adding carbon and MOS2, what we got was only this cubic phase of C2. Optical absorption, okay. So we just estimate the band gap using Doppler plot, that is not shown here. So we got approximately close to 2.4 electron volt for bare bismuth vanadium oxide, and also for bare Ce2O we got approximately close to 2.1 electron volt band gap. So so when we just add this molybdenum and also this one, also there is a slight shift in this absorption band edge threshold. So you can also see that one here. Okay, there is a red shift of that absorption band edge. And we also did the Raman spectra. Okay, so Raman spectra, from the Raman spectra also we just got monoclinic sealite structure of the bismuth oxide that you can just see from this Raman spectra of bismuth oxide. Similarly, so we can also identify the peak related to MOS2 also based on this vibration Raman spectra. Similarly, for cuprous oxide, okay, so we got this Raman spectra vibration for only this cuprous oxide C2O, okay, not any CuO. And we can also, because if we want to know the existence of this carbon coating, so this Raman spectra is a good tool. So we can also identify the G band and D band of this, the carbon that we coated on this C2O. Similarly, you can also identify the peak related to MOS2 also. Okay. So from these basic characterization results, we confirm that we prepared a monoclinic select phase of photoanode and then cubic phase of photocathode. So the most important thing here is this photoelectrochemical characterization. Photoelectrochemical characterization actually, okay, tell you the actual behavior of the prepared photoelectrodes, okay, towards this water redox reaction. So here we just followed four different photoelectrochemical tests to kind of identify different parameters from the experiments. For example, if we just use linear sweep voltammetry, you can just find the onset potential. I will tell you what is onset potential. And if you use electrochemical impedance spectroscopy, you can just extract the charge transfer resistance, okay. And also you can also identify the bulk charge transport. You can also identify different resistance involved in this process. And from the Mott-Schottky analysis, one can just estimate the flat band potential and what is the carrier concentration present in the material. And also you can also identify the type of electrodes, whether it is N type or P type. Everything can be extracted from this Mott-Schottky analysis. And before moving on to showing this photoelectric let me just spend few minutes on this flat band potential. So flat band potential is one of the important measure of any photoelectrode system. So why it is important? Because normally when you just bring a semiconductor and electrolyte medium, okay, For example, in this case, it's a p-type semiconductor. So when you just bring p-type semiconductor, okay, with an electrolyte medium, in this case, let's say water. So this electrochemical potential of this semiconductor and this aqueous medium will get equilibrated. So when they get when they are at equilibrium, so there will be some charge transfer taking place. Okay, so before this equilibrium, so after that we get this equilibrium state. So in this case, since it's a p-type semiconductor, electrons will be transferred from this liquid medium to the semiconductor. So the now semiconductor gets some extra electrons, okay, so close to the surface. So that we just represent the energy band diagram as downward band bending, okay. So that means it has excessive electrons at the surface. So that you get this downward band bending. And this band bending, because we just change the energy of this semiconductor close to the surface, this change in band, okay, energy or band bending results in built-in electric field creation. Okay, so we create electric field. So in this what is called depletion region width. Okay, so this built-in electric field is responsible for separating the charge carriers. If electron hole pairs are created, okay, holes are created here and electrons are created here, and these electrons will move towards this for p-type semiconductor. It will move because electron normally will move from higher potential side to lower potential side. So it will just will be transferred to the electrolyte, and holes will be transferred to the back electrode or back contact. So in this way, one can just separate the charge carriers. So flat band potential is nothing but, okay, so after this equilibrium condition, okay, so you just apply potential from the power supply. For example, this is potential state. So the external applied potential is in such a way that it will flatten this band from this bending to this okay level. That is, you just it just external applied potential at some potential, okay, this band will be flatter. So that potential is called flat band potential, because when the band edges or band is flat means there is no built-in electric field. So even if you just create electron hole pairs here, these electron hole pairs, okay, cannot be separated efficiently, and there is no chance that they can recombine very easily. So in such a situation, you will not get any current. So maybe if you just do your electrochemical test, okay, so this point something somewhere here for ideal case. So you get this is something close to flat band potential. If you know the flat band potential, you can also kind of construct the band diagram for given semiconductor material, for given electrode material. And second important thing is that if you have n-type semiconductor, okay, so this flat band potential should be more negative of the hydrogen evolution reaction, and similarly for p-type, it should be more positive. So what happens if it is not, for example, you can just see one example here. For they have p-type semiconductor, one with normal p-type and another one with tandem structure. And this is hydrogen evaluation reaction, because hydrogen evaluation reaction depends strongly, both these water redox reactions depend strongly on the pH. So at the pH 0, if you just look at, okay, so it happens close to 0 and it happens close to 1.23. That oxygen evaluation potential is 1.23 and hydrogen evaluation potential is close to 0. For this one, this flat band is somewhere here, potential is somewhere here, okay, that is it's not more positive, it is more negative than this oxygen evolution potential, whereas for tandem, it is more positive than this oxygen evolution potential. So if we have this kind of scenario, okay, before we just get the desired reaction, the band will be flattened, so no more electron hole pairs will be separated, so that will lead to reduction in photocurrent. So in that case, one has to create this band bending by just applying some external bias from the power supply. Okay, so that's the reason that when you just design your photoelectrode material, you should also consider about this flat band potential values. Okay, that is also, that's why this is one of the important necessary in photoelectrode or semiconductor photoelectrode system. So this is the setup that we use to test our photoelectrode materials. And let me just show you some of the results. The first one that you see here on the left side is linear sweep voltammetry. From this test, we can just measure onset potential. Onset potential means it is the potential. Okay, this is x-axis. Its plotted potential is plotted on the photocurrent density is plotted on the y-axis. So the potential at which this photocurrent starts evolving is called onset potential. Okay? So if you just look at this uh, uh, photocurrent results for this photoanode. So for bismuth vanadium oxide, the onset potential starts at 0.61, whereas if we just dope the material with molybdenum, we just improves the conductivity. So if you did improve the conductivity means you have more charge carriers, you have more transport of charge carriers. So that will just bring this onset potential more cathodic. That is, it is even better than this bare bismuth vanadium oxide. So when we just add this co-catalyst, it even shift this onset potential towards more cathodic side compared to this dope one. So you can just see this onset potential. So that means we get more photocurrent from this one, even at lower bias. You can also see we just turn on light here, okay, and then turn off light here. So you can just see quick response of this photocurrent when you just turn light on and light off. This is done at fixed voltage, I think 1.23 volt, because that is the water oxidation potential with respect to this reversible hydrogen electrode. So we also did some other photoelectrochemical test. This is the electromagnetic impedance spectroscopy in the previous slide. This is one of the important to just identify the resistance involved in the photoelectrochemical system. Okay. So normally after plotting this curve, one has to model, make some model by just fitting this curve. Okay, so it is under process, but qualitatively one can just tell you. Okay, one can just estimate that if you have smaller semicircle, meaning that it has a smaller interfacial charge transfer resistance. So you see that for compared to bare, okay, we just get smaller semicircle for this doped one with what is called co-catalyst. So that actually results in improved photo current as well as this improved onset potential. So we also did this Mott-Schottky analysis for this system, okay, for this three different photo electrodes. From that, we just estimated the flat band potential value. From this flat band potential value, okay, for N-type semiconductor, normally this curve will be okay, increasing upwards. So this kind of Mott-Schottky plate will tell you that this is N-type semiconductor. Maybe you will see for P-type that will be in opposite way. Okay, you have this downward slope, you have here upward slope. So that tells you that the material is N-type. That's one thing. From the flat band potential, okay, one can just estimate the band structure for N-type semiconductor. Okay, uh, if you just approximate, okay, this flat band potential will be more or less equal to the conduction bandage. Okay, so that if you just take this value, so you can just think that that is the conduction band of bismuth vanadium oxide. From the optical absorption, we know the band gap value, so that you can just measure. From that, we can just estimate the conduction valence band edge of the given semiconductor. So in this way, you can also plot the band structure based on these studies. Similarly, we did the same thing for photoelectrode. Okay, for photoelectrode, here we have three different systems. One is with bare, another is with this protection layer, and third one is with protection layer and this co-catalyst. So as expected, okay, so compared to bare, we just get some better performance for this combined system. And also from Mott-Schottky analysis, you can also see that we estimated the flat band potential values. So since this work is on a tandem structure, so to just measure the tandem photoelectrochemical cell. So what we need that we just do this photoanode measurement in 3 electrode setup separately, and photocathode PEC measurement in 3 electrode setup separately, and then we just combine these two. Okay, and when you just combine these two, the point that intersect both blue one is photoanode and red color is photocathode. This point is actually is the operating point. Okay, so the photocurrent that we just get from this one actually defines how much efficiency one can get from such system. Okay, uh, qualitatively one can also measure the photo voltage. Okay, even from this LSV curve also you can just measure the photo voltage from the onset potential. For photoanode, you just look at where this photocurrent start increasing from that to 1.23, because here you have this oxidation potential of water is taking place. So that voltage is roughly estimated as photovoltage, but this is not the exact way of measuring the photovoltage. But to okay, you can just roughly estimate how much photovoltage is generated by the semiconductor photoelectrode. So in our case, okay, so when we just combine these two systems, photoelectrode, photoanode based on bismuth and photocathode based on C, okay, we did with the different combinations, and we got for this combination we got the photocurrent the operating point current is about 0.25 milliamps per centimeter square. So even though this value is very low, if we just convert this one to efficiency, it will come close to less than 1%. But most of the systems that are reported in the literature also, okay, has efficiency of for such kind of system less than 1%. Okay, so there is, because here we need to still optimize the system. So actual, this is actually with electrode setup. So just measure the actual efficiency of the tandem system. So we just use 2 electrode setup without using reference electrode. So we just this is bismuth oxide and this is cuprous oxide, and then we just shine light using this solar simulator. And here at zero bias, okay, that's why it's called unresisted solar water splitting. Unresisted means without applying any external bias, how much current the system is producing. So that is the actual. That's what actually we wanted to work with, because here the value is very less. So one has to improve this photocurrent at zero bias, okay, to get better efficiency. So this is actually just to test the stability of the tandem system. So when we have this bare photon and photocathode, the system is not at all good. Okay, you get a zero current. Whereas for this combination, we get okay, some increase in current compared to this bare system. Still okay, because these are all ongoing work. Okay, still we are optimizing the system. Hopefully, we'll get some better photocurrent at zero bias. So the second part, okay, let me just go through it quickly. Okay, so this is about photo. Uh, uh, this work has been done by Mr. Varun Kumar. He is working as a senior research fellow in our lab. He has been working mostly on this photocathode materials based on copper oxide. So he is planning to use cuprous oxide, copper bismuth oxide, and copper, I think, iron oxide also. But he has started with this copper bismuth oxide. So he did a lot of experiment on this copper bismuth oxide as photocathode, and then he combined this system with bismuth oxide. So still work is going on. So we will show you some of the results that we got from CuB84 as photocathode along with this MOS2 as co-catalyst. So for this system, okay, CuB84 has a band gap of about 1.5 to 1.8 electron volt. It also has a p-type semiconductor, so it can be used for as photocathode in semiconductor photoelectrochemical system. And we also prepared this cuprous, copper bismuth oxide with hydrothermal method, and also we just coated MOS2, okay, that is commercially available, and you can just see that this is the SEM image of this copper bismuth oxide, and after coating this MOS2, you can see this flakes. Okay, so this is bulk MOS2. This is or single layer by layer. And from this also we just got some improvement compared to, because CuB84, even though it is an oxide material, it is not stable in presence of water, because this copper can be reduced, okay, and it will self degrade. So for that we need to either add some protection layer. This protection layer that we add in the form of co-catalyst. So in that case, we just got some improvement in the photocurrent when we just add this MOS2 compared to this bare this copper bismuth oxide. So from here also we just kind of did Mott-Schottky analysis and this EA spectra. So this EA spectra actually I didn't show the results here. We got the charge transfer resistance and charge transport in bulk. Everything is smaller than, for MOS2 system, it is smaller than this bare system. From the Mott-Schottky analysis, okay, we just got the flat band potential of about 1.1. That is really, normally the CuB84 is one of the so one of the good materials as photocathode, because it has high positive flat band potential. For N type, if you have more positive flat band potential, that is good for photoelectrode system. Similarly, for N type, if the flat band potential is towards minus side, that is cathodic side, so that is even good for semiconductor photoelectrode system. From this, we just constructed the band structure. From that band structure, we can just see that it is indeed the prepared material can indeed has the ability to split water into hydrogen, because this is only photocathode. So that can easily reduce water into hydrogen. So we just combined the CuP84, because last week only we just tried with bare bismuth vanadium oxide. The result is not promising, but we are just working on just to add some kind of protection layer at least. Hopefully we will get some results. So at zero bias, actually there is no current at all. You can just see this flat curve. When we just increase the bias voltage, that is, you can just see some increase in current. But what we wanted was actually just we want to test the system at zero bias. If we get some current at zero bias, that is uh, what we expected from this tandem system. So to summarize this PEC tandem structures, okay, so even though we got some photocurrent at zero bias, still more works are needed to stabilize the system and that's the summary from this tandem structure. Let me just spend 2 to 3 minutes on another topic, which is about perovskite solar cell. Okay, this work is done by Arun Kumar, research scholar in our lab. He has just started this work very recently, and because of this pandemic, he couldn't do any kind of lab work. And as most of you may be aware of that, this perovskite solar cell is one of the latest photovoltaic, and it's comes under third generation of solar cell. Okay, so this is on par with or it's better than this second generation solar cells, because it can produce efficiency of more than 22 to 25%. Okay, that is better than this silicon based thin film solar cell. Okay, that is available commercially on the market. So why it is called perovskite? Normally, if you just take polysilicon titanate, okay, it has a crystal structure of something called ABX3. So this perovskite also has the same crystal structure. That's the reason that it got its name. So in this ABX3 structure, A is cation, B is another cation. Normally this is metal. And X is halide, so it may be bromide, chloride, or iodide. So to just understand the stability of the crystal structure, so they use this Goldsmith tolerance factor. They just take the ionic radii of these different cations and anions. According to this one, if the tolerance factor is between this 0.8 to 1.1, that perovskite structure is somewhat stable. And if we get anything close to 0.9 to 1, so that structure is more of like cubic perovskite. So that's one thing. And in this perovskite, actually, okay, it is actually a good material to conduct both electron and hole. Okay, so when you just shine light, okay, so the electron hole pairs are generated or exciton is created. So one has to separate these charge carriers. In solar cell, we need to extract this photo generated charge carriers to the. So to just separate these charge carriers, okay, we just use this electron transporting layer and hole transporting layer. So this electron transporting layer will just kind of okay, easily separate the electrons from this photo generated charge electron hole pairs in the perovskite. So this will further okay transport this electron to the contact electrode. Similarly, this whole transport material will efficiently okay separate holes from this absorber layer. Okay, so in this way you can just separate charge carriers and then we can just send it to external electrodes, okay, to do some to apply it to some kind of load. So you have different types of perovskite. One is with mesoporous titanium dioxide, okay. Another one is with planar, and this is called normal structure, okay. This is similar to organic photovoltaic cell, so they just follow the same kind of architecture. And another one is called inverted structure, okay. So in inverted structure, okay, here we just deposit first this whole transport material on top of this flexible, so not flexible, transparent anode, and then we just have this absorber followed by electron transport layer. So here also we can have both the planar and mesoscopic structure. So this one have some, this structure has some advantages over this what is called normal structure. Uh, because of time limit, I don't want to go into detail. And let me just show you what is the current, what is the state of the art of this perovskite solar cell. You can just see that perovskite, okay, so now it can reach up to 25.5% efficiency with only perovskite. If we combine with perovskite with the silicon as tandem structure, it can even go up to 30%, okay. So now research community is in the process of commercializing this perovskite solar cell, and this is based on lead. Okay, so this is lead-based perovskite, and if you use lead, actually this lead actually poses some serious threat actually to the environment. So the research community, okay, they are just have some alternative to just avoid this lead in perovskite, and there are some alternatives to lead, okay, that can be used in perovskite. One of them is the tin. So our work is focusing on this tin based perovskite. So either you can use, in place of lead you can use different materials, but here we just prefer to use tin because tin and lead has more or less the same ionic radius. So of course you will get more or less close to the same structure as lead-based perovskite. Unfortunately, this tin-based perovskite efficiency, if you just look at the starting efficiency was 6%. Now, after optimization, they have reached up to 13% efficiency. Still, it is far from this lead-based. The main reason is that when you have this tin-based perovskite solar cell, the tin, okay, oxidation state, okay, it can just it's not stable, so it can just move from okay, change from tin 2 plus to 4 plus. So these tin ions act as a p-type, okay, it will just self-dope the material, so the material becomes p-type. So even on dark you get lot of dark current, okay, which in turn okay reduce the open circuit voltage. Overall it will affect the photo conversion efficiency, okay. But there are ways actually to just uh, overcome this self-doping issue of this tin-based perovskite. It has the potential to just at least compete with the lead-based in terms of efficiency, but still much work is needed. So my student is working on this theoretical based tin-based perovskite because of this pandemic. Okay, he was forced to do some theoretical work. Okay, so what he did was actually he used some open source software, SCAPS only software. With that software, he just tried to optimize some of the parameters theoretically. So what he did was actually he just played with thickness because thickness is also one of the important parameter. So he just optimized a lot of parameters and how this parameter affect the efficiency as well as this basic parameter like open circuit voltage and short circuit. For example, if you just look at this one, the photo conversion efficiency is decreased after 700 volt. Simultaneously, there is a decrease in open circuit voltage. So this has to do with something like recombination rate, because when the thickness is increased beyond the diffusion length of minority charge carriers or charge carriers, okay, so there is a high chance of recombination that will reduce the open circuit voltage, which in turn reduce the efficiency. So we can also do a lot of optimization based on these theoretical things. For example, he just voluntarily introduced some defects because prepare material in the lab, so obviously it should have a lot of defects. So when you just play with the defects, how it affects different parameters of solar cell, also you can see that. Obviously, if you have more defects, obviously it is detrimental to the photo conversion efficiency. That's also, you can also optimize. And also this playing with the metal contacts, this top metal contacts also. So one of the important parameter when you just okay, design your perovskite solar cells. Okay, that also affects. So based on his calculation, he found that both nickel and platinum, okay, has a better photo conversion efficiency compared to some of the standard material that we use as electrode contact. So out of nickel and platinum, because of platinum is expensive, we just suggest that nickel can be one of the alternative for these top metal contacts. So, so after optimizing all the parameters, okay, so with these optimized values, I didn't show you here, okay, so you can just see that after optimization, okay, there is a dramatic change in this efficiency, both efficiency as well as this short circuit current and open circuit voltage. He also did something extra beside this uh, what is called tin-based solar cell using zinc oxide as an electron transport layer. So this work actually he uses zinc oxide as an electron transport layer. He also played with the different electron transport layer, and he just came up with that out of different electron transport layer, this zinc tin oxide, okay, outperforms all the other electron transport materials that he chose to study in this work. Okay, so the reason is that it has high electron affinity. So because of that, you get better photo conversion efficiency for the system compared to all other systems. So with that, I would like to summarize this part. Here we just did computational analysis using SCAPS only software to predict the tin-based perovskite. As per prediction, so this tin-based perovskite theoretically can reach up to 25%. So by okay, for our system based on this tin sulfate, tin oxide as an electron transport layer, we need to just validate the results, okay, by doing experiment in the lab. Okay, so we hope at least we get some good results based on these theoretical studies. Okay, so so before ending my presentation, I'd like to invite you for this conference organized by our center. Okay, so the congress will start from next week. So we got some good speakers all around the world. So even though the registration is closed already, so you can still register as a participant. It's totally free, and you have also a chance to publish papers in some high impact journals, focus journals that can just check So please feel free to register for this congress. Okay, so that will be held next week. So finally, I would like to thank my funding agency. Okay, for providing funding for this project. Also, Dr. Grace. Okay, she is my collaborator for this funded project. I also thank all my research scholars, and also I like to thank Dr. Vasudevan from Dean Smith for giving this opportunities, okay, to interact with DHU people. Thank you very much. I'm very sorry if I took very long.
Okay, all right. Thank you, Professor Raja, for your great presentation in the area of solar energy conversion. And this is really a lot of work and very impressive. By the way, this is Dr. Fuda Ning from System Science and Industrial Engineering Department at Binghamton University. And on behalf of Dr. Muhammad Kasane, I would like to host the Q&A session now. So for the audience, if you have any questions, please feel free to unmute yourself and ask questions.
Professor Raja? This is Prabhu. I'm a graduate student here at Binghamton University. My question is on the first part of your research on water splitting. I think it is related to slide 5 or 6. I wanted to know, slide 5, I think. I wanted to know whether there is a use of an enclosure or a separator to collect
Obviously,
hydrogen.
obviously, in a typical photoelectrochemical cell, we need to use, because we haven't tested this hydrogen evaluation, actual hydrogen evaluation, oxygen evaluation, how much gases are evolved. Okay, so for that we need to use a membrane here, natural membrane. Okay, so that you have one compartment for photoanode, one compartment for photocathode, so you can just collect these gases separately. So obviously, there should. So this is just for a simple schematic. I just skipped that part actually, just to make you understand what is the system.
Yeah, very helpful. Thank you.
Any other questions for Professor Raja? Actually, I have a question, Professor Raja, regarding, yes. I think it's in the earlier presentation, probably in slide 7, if you can please go to the slide 7 there. So when you talk about the light absorption utilizing the nanostructure materials, may I know what are the specific materials that you utilize?
Actually, these are the ways proposed in the literature. So we haven't actually started any kind of nanostructure, but normally if you have kind of wires or rods, when you just shine light, when light is illuminated on such kind of structure, so there is that the light can get scattered multiple times. So you have this multiple scattering of light that will eventually lead to more prolonged optical interaction with the material. So thereby will lead to enhanced absorption. That's the reason. Compared to if you just take flat thin film. So if you just shine light, the light, okay, interaction volume or light, what is called interaction path will be very, very small. So if you just take such kind of system, the light will, okay, scatter multiple times inside the material. So which will eventually lead to higher absorption than normal material, that is the flat material. That's what I just wanted to make from here.
Okay.
So these are the general strategies employed actually. So we are going to stick with some of the strategies actually proposed here.
I see. Okay, thanks. Any other questions or comments? By the way, Professor Raja, would you please tap your email address into the chat window so that our colleagues and students can, send emails to you to maybe have some other follow-up questions and discussions after the meeting. Tap into the chat window will be of great help. Okay, all right. Thank you, Professor Raja, again for your presentation and sharing your research vision and insights into this solar energy field. I really appreciate that. And at the same time, I would like to announce our next speaker. So I'm gonna share the screen at this time. So our next speaker will be Professor Yingyi Zhao, who is an assistant professor at Binghamton University in the System Science and Industrial Engineering Department. And his talk will be electrospinning biometric scaffolds for tissue engineering. I believe Dr. Muhammad Kasane will share this seminar poster earlier next week. So please feel free to send this poster to your colleagues and students. And we look forward to meeting all of you next Thursday. Okay, so I believe this is the end of today's seminar. And again, thank you very much for participation in our joint seminar series between Binghamton University and VIT. And we look forward to seeing everyone next Thursday. Thank you very much. Have a good one.
Thank you. Bye-bye.
Thank you, Dr. Raja. Thank you, Dr. Professor Fuda. Thank you.
Thank you. Bye now.
Bye.
Thank you. Thank you.